Okay, so picture this. On one side, you've got our incredible planet-spanning power grid. It's a total marvel of engineering. And on the other side, the sun, which, every now and then throws a massive electromagnetic tantrum right in our direction. Today, we're diving into the front line of that conflict, the really complex engineering puzzle of how to protect our most critical infrastructure from the fury of a solar storm. It sounds like something out of a movie, right? Could a storm in space actually black out your city? But here's the thing, it's not science fiction. The threat is real, so real that some of the best minds in electrical engineering are working around the clock to make sure the answer to that question is always a firm no. So how on earth do you shield a machine the size of a continent from a solar flare? Well, let's get into it. So first things first, we've got to understand the enemy. This isn't about heat or anything you can see. No, this is an invisible threat, and it attacks the very laws of physics our power grid is built on. It all kicks off with something called a geomagnetic disturbance, or GMD for short. When a huge eruption from the sun smacks into Earth's magnetic field, it literally makes that field wobble and shake. And for us down here on the ground, that magnetic chaos creates a powerful electrical field. Our thousands of miles of transmission lines, they basically act like giant antennas, soaking it all up. That process creates these things called geomagnetically induced currents, or GICs. Now, you have to remember, our grid is designed for high-voltage alternating current, AC, that nice, smooth, predictable wave. But GICs, they act a lot more like direct current, DC. It's this slow, heavy, rogue current. And when you try to force DC into a system that's built from the ground up for AC, well, that's when really bad things start to happen. This diagram here shows you the problem perfectly. That GIC flows along the power lines, and it looks for the easiest path to the ground. And guess what that path is? Right through the neutral connection of these huge, expensive transformers. This unwanted DC current basically shoves the transformer's magnetic core into a state called half-cycle saturation. A good analogy is like trying to pour water into a bucket that's already half full of concrete. It just can't work right. The transformer starts to overheat like crazy, it vibrates, and eventually it can just completely fail. Okay, so the problem is a rogue DC current where it shouldn't be. So the engineering solution has to be like a bouncer at a club, right? Something that lets the good AC current in but slams the door shut on that troublemaking DC current. And the idea behind the solution is it's beautiful. It's so simple. On the left, you see the problem we just talked about. The GIC has a wide-open highway to the ground right through the transformer. But on the right, you see a device has been put right in that path, and it just breaks the circuit for that GIC. This clever fix is called a neutral blocking device, or NBD. So what is an NBD? At its heart, it's basically just a big capacitor. And here's the cool part. To a slow-moving, DC-like current like a GIC, a capacitor looks like a broken bridge. It's a dead end. It blocks the flow completely. But to our normal, fast-moving 60 Hz AC current, the capacitor is pretty much invisible. It just lets it pass right on through. It is the perfect electrical gatekeeper. But, when you're dealing with high-voltage engineering, nothing is ever quite that simple. An NBD isn't just a capacitor in a box. It's a whole system with its own built-in safety features. Think of them like an electrical relief valve. We're talking about things like a metal oxide varistor or a spark gap, and they're designed to protect the NBD itself, which, funny enough, leads us right to the heart of our story. Okay, so this is where the real engineering puzzle starts. You've just invented this great device to protect against a very specific and pretty rare event. But what about the other 99.99% of the time? How do you make absolutely sure that your cure isn't actually worse than the disease? I mean, check out this quote from the Electric Power Research Institute, or EPRI. They basically said, look, we're not even testing if the NBD works during a solar storm. We're going to assume it does. What they really cared about was everything else. They were on the hunt for any unintended consequences of putting this new piece of gear into an already incredibly complex system. Think about it. A truly massive solar storm might happen once in a generation, but a ground fault from a tree branch falling on a line or a lightning strike? That stuff happens all the time. So the big question is, does this new protective device suddenly become a weak link during one of those really common events? Does it accidentally make a simple problem way, way worse? Answering that was absolutely critical. So how do you find out? You can't just install thousands of these things and cross your fingers waiting for something to go wrong. No, You have to get clever. You have to build a virtual world and then try to break it in every single way you can possibly imagine. So that's what EPRI did. They used some seriously powerful software to build a super detailed model of a transmission system. And this wasn't just some diagram, okay? This was a living, breathing, virtual grid where they could simulate disasters down to the microsecond. And then they just threw the kitchen sink at this virtual grid. I mean, they simulated everything you can see here. Huge faults right next to the NBD, tiny faults far away, faults that hit all 3 power lines at once. They even simulated totally normal, everyday stuff, like just switching on a transformer, to see if the NBD would somehow get confused. And right here, we get to see one of those crash tests in action. The top graph shows the grid voltage going haywire during a fault. But look at the bottom graph. See that rising blue line? That's the total energy being soaked up by the NBD's little safety valve. And that dotted line? That's its maximum limit. You can see exactly what's about to happen. So the safety valve in the simulation, it was rated to handle a maximum of 33.32 kilojoules of energy before it gave up the ghost. It's a very specific, calculated number. Engineering is all about the numbers, and in this test, this is the number that really matters. So what was the result? Well, during this massive fault, that energy limit was blown past in just 0.02 of a second. The safety valve fails, the entire NBD is bypassed, and all that crazy fault current flows harmlessly to ground. And here's the crucial point. This isn't a design flaw. This is the design. The NBD is literally built to sacrifice itself to save the multi-million-dollar transformer it's there to protect. So after running dozens and dozens of these virtual crash tests, a really clear picture started to emerge. And it all comes down to one of the most important principles in all of engineering: designing for failure. This table just sums it all up perfectly. Okay, scenario 1, a solar storm. The NBD does its job, it blocks the current, and boom, the transformer is protected. Scenario 2, a really severe ground fault. The NBD knows it's out of its league, so it fails on purpose and gets out of the way. And guess what? The transformer is protected. And in the third scenario, a minor fault somewhere else, it does nothing. It just sits there ready for the big one. See the pattern? In every case, the #1 mission, protecting that priceless transformer, is achieved. And that right there is what brilliant engineering looks like. It's not just about building something that works. It's about building something that understands the world it lives in. It's having the foresight to know exactly when to act and, just as important, when to make a graceful and safe exit. This entire system that we all depend on every single second is humming along because of countless little devices just like this one, each the result of thousands of hours of this kind of painstaking what-if testing. It really makes you wonder, doesn't it? What other invisible storms, what other silent threats are engineers quietly working to protect us all from right this very minute?